In this video, I want to talk about least squares solutions for systems of equations. Let's suppose we have ax equal to b, and we know this is an inconsistent linear system, so it does not have a solution. However, we suspect the inconsistency can be caused by errors in either the entries of the matrix A or the vector B. But since there's no exact solution possible, we want to find a vector x that comes as close as possible. So we want to get a solution that's as close as we possibly can get. So we're looking for a vector x that's as close as possible, and this is known as our least squares solution. The vector b minus ax, so what we want our system to be equal to minus what we're getting it to be when we talk about as close as possible, this is our least squares error vector. And the norm of that vector is called the least squares error. And when we talk about as close as possible, we are trying to minimize this. We want this value, the length of this vector, to be as small as possible. How we're going to do this is using what's known as the normal equation. The normal equation multiplies both sides by A transpose. We have A transpose A times x equal to A transpose B. And it turns out for every linear system, this system right here, this normal equation or normal system, is consistent. The solutions to this system are the least squares solutions. So let's look at some examples. Here I have my system x1 minus x2 equal to 4, 3x1 plus 2x2 equal to 1, and negative 2x1 plus 4x2 equal to 3. So my matrix A is my coefficient matrix. 1 minus 1 in the first row, 3, 2 in the second row, and negative 2, 4 in the third row. My vector B are my constant values. In this case, 4, 1, and 3. So we need to start by finding two things. First, A transpose A. The transpose switches rows to columns and columns to rows. And then we can multiply that by my matrix A, my coefficient matrix. When we do, we get the matrix 14 minus 3 minus 3, 21. We also need to find A transpose times B. So we'll have A transpose times my constant vector 4, 1, 3. And when we multiply that, we get the vector 1, 10. So to actually solve this system appropriately, to do our least squares solution, we're going to solve the system 14, negative 3, 21. We have our vertical bar, and then 110 on the right-hand side. And we need to row reduce this. We can do it by hand or using technology. But when we do get a solution of 17 over 95 and 143 over 285. So my least squares solution is going to be these two numbers. 17 over 95 for x1, 143 over 285 for x2. Now that we have our least squares solution, let's try to find the error. B minus ax. B was my vector 4, 1, 3. Minus the matrix A, which was 1, negative 1, 3, 2, negative 2, 4, times x, the solution I just found. 17 over 95, 143 over 285. Well, this is 413 minus, when I multiply these two matrices, I get negative 92 over 285, 439 over 285, and 95 over 57. And once we do our subtraction, 1232 over 285, negative 154 over 285, and 4/3. So this is my least squares error vector. To find the actual error, we need to find the length of this vector, or the norm. And I won't show the steps, but we do get that it is approximately 4.556. So let's look at one more. This time, I have a system of 3 equations with 3 variables. So my matrix A comes from the coefficients: 3, 2, minus 1, 1, minus 4, 3, and 1, 10, minus 7. My vector B comes from the constants, which are 2, minus 2, 1. So we start the same way we did before. We need to find A transpose A, which I won't write out the steps for, but we can use technology to multiply these matrices or do them by hand. We get 11, 12, negative 7, 12, 120, minus 84, negative 7, minus 84, 59. We also need to find A transpose B, which once again you can do by hand or using technology, and we get 5, 22, negative 15. So the system I need to solve has A transpose A on the left, and A transpose B on the right. And then we can use technology or reduce this by hand. When we do, the first column is 1, 0, 0. The second column, 0, 1, 0. The third column is 1 over 7 minus 5 over 7, 0. And then on the right-hand side, we have 2 over 7, 13 over 84, 0. So this one actually has infinitely many solutions, which is entirely possible. My equations: x1 plus 1 over 7x3 is equal to 2/7. x2 minus 5 over 7x3 is equal to 13 over 84. So I can rewrite this as x1 is equal to 2 over 7 minus 1 over 7 x3. x2 is 13 over 84 plus 5 over 7 x3, and x3 is equal to any value. So any solution that satisfies this set of equations right here will be a least squares solution to this system. So this one has infinitely many possible least square solutions. So let's try to find our error vector, b minus ax. B was the vector 2, minus 2, 1. A was 3, 2, minus 1, 1, minus 4, 3, 110, minus 7. Over here I have 2 over 7 Minus 1 over 7, I'm going to use the letter t instead of x3 just to make things a little bit simpler. 13 over 84 plus 5 over 7, t, and then x3. Once again, I'm just using the letter t to make things a little simpler. And if we work this out and do this multiplication and subtraction, we actually get the vector 5 over 6. Minus 5 over 3 minus 5 over 6. All of the t's actually cancel each other out. So since b minus ax does not depend on t, all of our least squares solutions are going to produce the same error vector and the same amount of error, which is going to be 5 over 6 times the square root of 6.